We're going to get started here in just a second. My name is Rick Wesson, and my co-presenter is Laura Sheble. It's always a pleasure to come and present these kinds of things. I really enjoy the feedback that we get from the community in trying to think about new ways of addressing some of the issues that we have in cybersecurity today. I said it, so I'll probably have to drink later. Yeah, I got one. I don't think we'll say it the rest of the talk. So at any rate, my name is Rick, and I'm the CEO of this little company called Support Intelligence. My co-presenter is also the editor of Misinformation and Mass Audiences. I'm going to butcher the title. This just came out today, and the series editor, Andrew Dillon, is also one of our guests in the audience. And so this is some of their work. It appears to be a pretty interesting book on a bunch of different papers that folks have written on this topic. And if anybody sees Gotti, he needs to go get one. So apparently I got the first autographed copy. And if you guys want to check it out, just let me know. I'm more than happy to let you play with the book. So today, Laura is going to start us off. She has got a PhD from University of North Carolina, is that right? And she's currently at the School of Information Sciences in Wayne State. And she's going to do the beginning of our talk, so give her a warm welcome.
Thank you very much. I'm going to give the 10,000-foot overview of the starting problem. And with the starting problem, we're conceptualizing how we approach identifying malware through a model. Some of the potential benefits of posing this as a model is we expect models to orient our perspectives on problems, and they can help us reformulate the questions we've been asking or potentially develop new questions that we might ask. They can also identify important elements. What should we look at? What should we pay attention to? And what should we let fade into the background? A model might be used to define relationships between those different elements that we choose to look at. And a lot of times these relationships will be expressed either as classifications, or sometimes we might use an equation, a mathematical equation, to express the relationships. Further, the models can guide our analyses and help us diagnose and suggest treatments or interventions. One kind of classic prevalent model that many people are familiar with would be that of disease and intervention in medicine. And with this, it's essentially a linear model where at the beginning there's an exposure to pathogens or some sort of underlying issue that is working through biological mechanisms and expressed as a disease in humans or other creatures. And so this model tells us that we look at the disease, we can make a diagnosis, and then apply a treatment or other type of intervention that in turn works through biological mechanisms and leads to either recovery or improved health status of the patient. And this model has been very effective in helping us approach many problems in health and across a wide variety of domains. Classically, we can think of the case of antibiotics, where an infection can be treated with an antibiotic and then the infection clears. A little bit more in the public health domain, we can think about water treatment and sanitization, where we have different types of pathogens and particulates in the water that we clean and filter through our water treatment process and thereby prevent infections. And they can take other forms, for example, to prevent malaria, that we can use mosquito nets and then thereby preventing the malaria. However, when looking at some of the most pressing health problems today, such as obesity and depression, And these are types of health conditions where we can't identify a single underlying causal factor that we can, with a pathway where we can have an intervention. And because of our lack of ability to find that single underlying factor, and where we actually, through our research, know that there's a multiplicity of factors, that genetics, environment, behaviors, all contribute to these health conditions, and also that there are feedback loops. And so one of the ongoing processes in the field of health and medicine is to try to push from the linear model into a model where we're thinking of health and health behaviors in, as dynamic processes and dynamic systems, and considering how things change over time and how the factors interrelate. And so while we had a very successful model, in cases where we find the limits of its efficacy, it's time to try to push towards developing new models. So how is this relevant to protecting our networks? In some senses, from a very simplified perspective, we can view our current approach to diagnosing malware as a model that includes both dynamic and static analyses. And dynamic analyses, as we heard in the last talk, and then playing in concert with static analyses, for example, where we look at key signatures and compare these to blacklists to see if they're among our known pathogens. Some current challenges with a model that employs these two approaches together are on the static side. There's a lot of work to camouflage the key signatures, and therefore they are blocking our ability to identify on the blacklist and polymorphism more generally. And on the dynamic side, that folks who are working to develop malware are trying to look for evidence that the malware is being run in a detection environment, and also, for example, using timers so the malware sleeps and times out past what the environment is set to run. So with the starting problem, this model looks surprisingly similar to the last one, but Rick will go into detail in how it differs. And how we're conceptualizing the difference is going from a static environment to what we think of as a hyperstatic environment. And also with this, going to a more general level of extraction. And with this, the features of the program are not extracted and they are more generalized. The benefits we get from going from the starting problem model is that there's a greater tolerance for variation when identifying malware, and also that this variation leads to filtering out more of the programs that would be sent for analysis in the dynamic environment. And Rick?
So we actually have presents for you all. This is the interactive portion of our presentation. And for those people that don't know, I have a farm in the Bay Area, and what we're passing out is various kinds of seed. You get to take these home and plant them, and if you ever want to feed me some of this stuff, I'd be more than happy to stop by. So how does seed have to deal with this concept that we're calling the starting problem? And what we have, or what we're trying to propose, is a new conceptual model for thinking about malware. And I'm going to propose that all of the stuff in these little seed packets is actually code, right? This is a little computer program. It doesn't look anything like what you're going to get. So if you open up this packet, you have a little round ball inside, and that doesn't look at all like look like an okra plant, right? Doesn't look like the okra fruit, doesn't look like the okra plant. And that's why they put the picture on the outside, because you wouldn't know what it is. Now, you would be able to tell that it's different from this. This is actually lettuce, as you would know it. And the seeds are completely different. The plants cannot interoperate, right? You cannot have the seed pollinate an okra plant. Doesn't work that way. However, if you open up your packet, and I encourage all of you to reach in there and grab some of these things, and the interactive part is to show some of them to your neighbor, you'll see all of your seed is different. And it's different for a reason, because it has an environment. You cannot take the DNA material out of one kind of seed and put it within another kind of seed. It is tied to its environment. The code inside of it is tied to its environment. And so if you were to take, let's say, some carrot seed and take the DNA out and replace this okra seed's DNA with it, it would not grow. And it wouldn't grow because all of the proteins that are around this seed coat influence the growth of that DNA into a plant. And so the problem, which I'm trying to call the starting problem, is how do we know when we can run code without running it? The previous presentation, these gentlemen have done some fantastic work on running code and telling you everything about that code and what it's going to do if you were to run it in a non-protected environment. And so it's a real asymmetric problem for defenders. There are a bunch of biological metaphors in your hand for this. So we're going to try and approximate what the software is going to do without running it. And this is a form of static analysis. Laura and I are calling this hyperstatic because we're going to take away all the features. So we're not going to extract anything from the programs, right? We know about sandboxing it. We know about the static analysis or unpacking. So my proposal is that we're going to draw it. And we're going to draw it using the same technique that the seed stores its DNA in, okay? So I'm trying to paint the picture for the code that you see as binary, okay? And what we're going to do is we're going to use this technique called a spacefilling curve, which is the same technique that all the DNA in all of our cells and all of our little seeds is organized so that it does not tie itself into a knot, which is very important. There's a whole bunch of diseases you get if the structures of your DNA are malformed, and if that happens at the embryonic stage, it results in death. So this is probably one of the most critical algorithms that's running in your cells, and each one of you has about 3 trillion versions of it that all actually execute the same. This is some of the oldest natural algorithms on the planet, and we're going to use that to organize a binary. And when you do, you get all of these features. It's a strange little artifact of using space-filling curves to take a one-dimensional object and turn it into a two-dimensional object. In our DNA, the organization is in 3 dimensions. This is a little faster in 2. So what do we get when we can do this? We get programs that are turned into numbers in this thing called a phase space. Phase space is a multidimensional, math. It's a multidimensional, you could think of it as a matrix place. And 512 bits is being used to describe these objects that we call programs. And 512 or 64 bytes is a little long for people to type. So I've done some more math and reduced it down to 63 bits for human consumption. 1 bit is reserved for the evil bit, if anybody's from the IETF and remembers that stuff. But the whole point is that what we're going to do is we're going to let data find itself. And what does that mean? It means that the okra seeds are only going to make okra, and they're going to look like okra, and it's going to be okra. And you eat it, it's going to have okra seeds inside of it. It's not going to be a tomato. Tomatoes are going to make tomatoes. And that's what I mean by data finding itself. These things do not make different things. They do not interoperate, right? It takes enormous amounts of time for them to transition into something else. And we will see that as well. So we can do this with many different kinds of data. We can do it with web content, scaffolding. We can use that scaffolding to locate phishing pages without even knowing who's phishing who. This is data finding data. We can organize email, spam, and finally, what we're proposing today is around file safety. It's about understanding when a program is evil or good without having to run it. And being able to do that very fast. And hence my question to the gentleman before us, our average analysis time is 1/2 millisecond per core. Ideally, we run on GPUs or FPGAs, but also happens to run on CPUs. So the idea is that we're taking software, we're turning it to an image, and then we're doing data racism. We are organizing everything into how it looks. And so, when we do this, we can take them all, stack them together, and make a movie out of it. And I can show you what this particular threat looks like. And this is what they're changing to get it through our defense systems. From this, we can also understand, I don't know if you guys can see it, but the MD5s run across the very top. We can understand which part of this program isn't changing, and we can use it to write a signature. And I'm going to tell you a little later about the hundreds of thousands of signatures that we've written using this technique. Sorry, I feel like these are home movies, and I don't know if it's cool or not. I can stop it here. Okay, well, we'll take that as maybe show me another. Okay, we'll try this one. I've got a few of these, and I'm not sure of my time. 7 minutes. Oh, awesome. Yeah, okay. So this one's a little harder. You'll see the MD5s going across the top, and it changes kind of like in big chunks. You can't actually see it. It's hard to find, but there's a little bit down there on the left-hand side that's going to change, and then the whole thing, right? So you want to write a signature for this. The part that doesn't really change is up here in this corner. All we're doing, all this process is we're taking every byte in the file and turning it into a grayscale pixel. Okay, this is the simplest. We have a question?
Don't you need just tons of samples to do this?
The question is, do we need tons of samples to do this? I have tons, and that's how it started. You know, I have tons of websites to do this. It seems like everything wants to have it done, and so the efficacy that we have with this is that we can do it to everything, right? So we can do it on our network streams, we can do it on every file that we come in contact with, you can do it on every JavaScript, every web page that you view, and the amount that you pay for it in CPU is very low. Right? It's not a big deal to do this. Usually your network traffic transit time is longer than this calculation. Now this calculation happens to also be a very intense calculation for a CISC CPU. But I didn't invent it, DNA invented it, or nature invented it, and so it's highly parallelizable, and it runs like lightning on a GPU or FPGA. We designed, and I'm not going to get into some of this, we designed the distance metrics so that we don't have to do KD trees. I don't know if anybody's ever had to write programs and try and do distance metrics with KD trees. It's a giant pain in the ass. It's completely fucked up to do things at scale. We've got hundreds of millions of malware samples, and you just can't put that in a database. So all of our identifiers, of which I'm more than happy to talk about afterwards or tomorrow, are just bit shifting math. So it's just shifts to measure distance, and then it's Jacquard distance or Levenstein distance to understand how far away two pieces of code are. All right, so here's one that I can't write a YAR signature for. And this is a cluster, and it kind of gives you a sense, just every single MD5. So each image is a frame in the movie, right? And this cluster is massively deep. And this is the technique. They're using an algorithm to obfuscate their code and their data sections in this particular program. And that algorithm is detectable, and all of this falls into the same cluster. And it isn't, it's not in another cluster, like JavaScript or another architecture. So back to the seed is the x86 code. It looks like x86 code. And it doesn't look like ARM code. It doesn't look like JavaScript or HTML. Every kind of data looks different. It has different packaging. It has a different environment. And you can't take a piece of JavaScript and make it look like a PE. It doesn't happen. It's part of the nature of its underlying data. And you can't escape it, just like you can't escape it in a seed, and you can't make an okra seed that grows tomatoes, or vice versa. That is how our world is organized. And so, one of the things that we tried to do, this goes on for at least 15 minutes, one of the things that we tried to do is generate some concept of proving in round trip. So I don't know if folks are on Yara Exchange. I'm sure some of you are. Maybe some of you are on CW. I made a bunch of Yara signatures available for free. And so I took 12,000 of these clusters that we generated and generated Yara signatures for them and published that. And so somebody took those 12,000 Yara signatures and ran them against 1 million of their samples that they got, plus a bunch of operating system files and a bunch of goodware. And so out of that, I got 87 hits that were not in those clusters, which was pretty much 6 sigma, almost 5 nines of accuracy, just from the Yara signatures. So then we took the false positives and clustered them, and they fell into a different cluster than the Yara signature was worked for. And so if you can do those 3 steps, right? Most people want to just play with Yara signatures. They think that drawing pictures of their code, they're just not ready for that yet. And that's why we're giving this talk, is to try and get people more interested in drawing their code. And so we got an accuracy just with, including the false positives of 99.99%. And we're able to do that at essentially PCI 3 bus speeds. And so if you have a problem and your limit is saturating the PCI bus, I feel like it's a win. Okay, so that's the bulk of our presentation. And Laura and I will be around for the next couple of days. We'd be more than happy to take your questions or talk about what we're trying to do with these ideas. We're certainly interested in your feedback, and that's why we wanted to come and present this kind of stuff. So, thank you. And if you want more seed, Laura has it. Thanks. So, oh, and did you have any questions? Because do we have a minute?
We have, yeah, sure.
Okay, so we can take one question.
One or two quickies.
Yeah.
Is the primary use here just to find variants of known bad? Is that its primary use case, or is it to look for bad heuristics?
The primary use case that I find it useful for is it's an unknown locator. So like if you want to write a blog post, you can just sort through my daily report, find something that no one knows about, and there's something good to go and throw at the world. And one more? One more question we have time for? Oh, okay. Come on, Jordan. Did you have a... Is this yours?
Yeah.
Oh, yeah. Thanks.
I saw more than one question. That's it. That's fake news. All right.
Thanks, guys.
He's been talking about that stuff on CW for years, but I've never seen the videos. Like, I have all the Yara stuff. I've done the same thing. I'm running against my Yara packages and all the malware I have sitting on terabytes and terabytes of garbage.
Yes.
And that's pretty dope. I'm just sitting here like wondering, like, how can I apply this as a filter to my network? Like, do I need like Rain Man to stare at it and block things? It's awesome.
Works for me if it works for you. Let's see.
Up next, the inimitable Jordan Wright.
Oh,